When sizing disconnect and overload protection for motors controlled by variable frequency drives, or VFDs, it is important to note that the tables 430.148 through 430.151 in the National Electrical Code do not account for the higher amperage ratings of VFD compared to the motor horsepower ratings. Therefore, when using a VFD, consider the following guidelines to ensure proper protection. First, the motor disconnect should be sized for the maximum current drawn by the motor and VFD combination. Typically, this corresponds to the maximum current rating of the VFD itself. Secondly, overload protection should be set to protect both the motor and the VFD. This can be achieved using either a thermal overload relay or an adjustable electronic overload device. Regarding the method of sizing the disconnect and overload protection for motors with VFD, there are multiple approaches to consider. One approach is to use the VFD amperage rating. This involves determining the maximum current drawn by the VFD, which is usually higher than the motor's nameplate horsepower rating. Use this maximum current value to size both the disconnect and the overload protection. Another approach involves using the motor's horsepower ratings and applying a correction factor, sometimes referred to as a fudge factor. First, determine the appropriate sizes for the disconnect and overload protection based on the motor's horsepower ratings using tables 430.148 through 430.151. Then, multiply these values by a fudge factor to account for the higher amperage rating of the VFD. A common fudge factor is 1.25, but the exact value may vary depending on the specific VFD type and application. For specific recommendations, if using a VFD to control multiple motors, take into account the total load current when sizing the disconnect and overload protection. Always refer to the VFD manufacturer's recommendations for specific guidance. Furthermore, it is always recommended to consult with a qualified electrician for assistance in sizing and selecting the appropriate disconnect and overload protection devices. The disconnect is meant to de-energize the circuit for maintenance. The overload is meant to protect the motor and conductors from an overcurrent condition. There are several factors that go into sizing the proper components. Let's begin by discussing the motor disconnect. As mentioned before, the motor disconnect should be sized for the maximum current drawn by the motor and VFD combination. In most cases, this will be the VFD current rating. However, it is also important to check the motor's nameplate to confirm the full load amps, or FLA, to ensure the VFD is rated appropriately for the motor. You should also consider the application of the motor to see if there may be any unusual or high starting or running currents. The NEC requires that the disconnect have an ampere rating of at least 115% of the motor's full load current rating. This is found in section 430.110. It also requires that the disconnect be able to interrupt the motor's locked rotor current. The locked rotor current is the current the motor will draw when it is first started. This current can be several times the motor's full load current. After determining the motor's full load current, multiply this value by 1.15 to obtain the minimum ampere rating for the disconnect. Ensure that the disconnect you select has an ampere rating that is equal to or greater than the calculated value. This will ensure that the disconnect is capable of safely carrying the motor's full load current and is code compliant. Next, make sure the disconnect is able to interrupt the motor's locked rotor current. This is especially important for motors that have a high locked rotor current. After determining the motor's locked rotor current, select a disconnect that is rated to interrupt that amount of current. This will ensure that the disconnect is able to safely interrupt the current if the motor is stalled or experiences a fault. Now let's discuss overload protection. Motors should have overload protection to protect the motor windings from overheating and failing. Overload protection devices are designed to trip and de-energize the motor circuit when an overload condition is detected, preventing damage to the motor. There are two main types of overload protection devices: thermal overload relays and electronic overload relays. Thermal overload relays are the most common type of overload protection device and use a bimetallic strip or eutectic alloy to sense motor current. When the motor current exceeds the relay set point, the bimetallic strip or eutectic alloy heats up and bends or melts, causing the relay to trip and de-energize the motor circuit. Thermal overload relays are relatively inexpensive and easy to install, but they are not as accurate or adjustable as electronic overload relays. Electronic overload relays use a current transformer to sense motor current and a microprocessor to analyze the current and trip the relay if an overload condition is detected. Electronic overload relays are more accurate and adjustable than thermal overload relays, and they can provide additional features such as ground fault protection and phase loss protection. However, electronic overload relays are more expensive than thermal overload relays. When selecting an overload protection device, it is important to choose a device that is properly sized for the motor. The overload protection device should be sized to trip at or below the motor's full load current rating. The full load current rating is the current that the motor is designed to draw when it is operating at its rated horsepower and voltage. The full load current rating can be found on the motor's nameplate. To size the overload protection device, multiply the motor's full load current rating by 1.25. The result is the maximum current that the overload protection device should be set to trip at. For example, if a motor has a full load current rating of 10 amps, the overload protection device should be set to trip at or below 12.5 amps. Select an overload protection device that has a trip current that is equal to or less than the calculated value. This will ensure that the overload protection device will trip and energize the motor circuit before the motor is damaged. When selecting an overload protection device, it is also important to consider the motor's service factor. The service factor is a measure of the motor's ability to operate at loads higher than its rated horsepower. Motors with a service factor of 1.15 or higher can operate at loads up to 15% higher than their rated horsepower without being damaged. If a motor has a service factor of 1.15 or higher, the overload protection device can be sized to trip at up to 125% of the motor's full load current rating. However, it is always best to consult with a qualified electrician or engineer to determine the appropriate size for the overload protection device. In addition to overload protection, motors should also have short circuit protection. Short circuit protection devices are designed to trip and energize the motor circuit when a short circuit occurs, preventing damage to the motor and other electrical equipment. Short circuit protection devices include fuses and circuit breakers. Fuses are one-time use devices that melt and open the circuit when a short circuit occurs. Circuit breakers are reusable devices that trip and open the circuit when a short circuit occurs. Circuit breakers can be reset after they have tripped. Fuses are typically less expensive than circuit breakers, but they must be replaced after they have blown. Circuit breakers are more expensive than fuses, but they can be reset after they have tripped, so they do not need to be replaced. When selecting a short circuit protection device, it is important to choose a device that is properly sized for the motor. The short circuit protection device should be sized to trip at or below the motor's locked rotor current. The locked rotor current is the current that the motor will draw when it is first started. The locked rotor current can be several times the motor's full load current. To size the short circuit protection device, consult the NEC table 430.52 to determine the maximum allowable size of the short circuit protection device. Then select a short circuit protection device that has a trip current that is equal to or less than the maximum allowable size. This will ensure that the short circuit protection device will trip and energize the motor circuit before the motor or other electrical equipment is damaged. The NEC outlines these ratings in Article 430. When using a VFD with a motor, the VFD will have its own current rating that may be higher than the motor's full load current. In this case, the disconnect and overload protection should be sized based on the VFD current rating, not the motor's full load current. This is because the VFD is the device that is actually supplying power to the motor, so it is the VFD current rating that determines the amount of current that is flowing through the circuit. However, it is also important to check the motor's nameplate to ensure that the VFD is rated appropriately for the motor. The VFD should be rated to supply at least the motor's full load current, and it should also be rated to handle the motor's locked rotor current. The specific requirements for sizing motor disconnects and overload protection with VFD can vary depending on the application and the local electrical codes. Therefore, It is always best to consult with a qualified electrician or engineer to ensure that the motor disconnect and overload protection are properly sized. Here's a more detailed breakdown of the considerations and steps involved in sizing motor disconnects and overload protection when using VFD. Firstly, determine the motor's full load amps, or float, from the motor nameplate. This is the current the motor draws at its rated horsepower and voltage under normal operating conditions. Secondly, determine the VFD rated output current. The VFD manufacturer will provide this information in the VFD documentation. This is the maximum current the VFD can supply to the motor continuously. Thirdly, compare the motor FLA and the VFD rated output current. If the VFD rated output current is higher than the motor's FLA, use the VFD rated output current for sizing the disconnect and overload protection. If the motor's FLA is higher than the VFD rated output current, which is uncommon, the VFD may not be suitable for the motor, and a different VFD with the higher current rating should be selected. Fourthly, size the motor disconnect. The motor disconnect must have an ampere rating of at least 115% of the motor's full load current, as per NEC section 430.110. However, when using a VFD, the disconnect should be sized based on the VFD rated output current if it is higher than the motor's FLA. Calculate the minimum disconnect size by multiplying the VFD rated output current by 1.15. Select a disconnect switch that has an ampere rating equal to or greater than the calculated value. The disconnect must also be capable of interrupting the motor's locked rotor current, or LRA. The LRA is the current the motor draws when it is first started, which can be several times the motor's FLA. Verify that the selected disconnect switch has an interrupting rating sufficient to handle the motor's LRA. Fifthly, size the overload protection. Overload protection is intended to protect the motor from overheating due to excessive current draw. When using a VFD, the overload protection can be provided by either a separate overload relay or by the VFD built-in overload protection. If using a separate overload relay, it should be sized based on the motor's FLA, not the VFD rated output current. The overload relay should be set to trip at or slightly above the motor's FLA, typically at 115% to 125% of the motor's FLA, depending on the motor's service factor. If using the VFD built-in overload protection, the VFD overload protection parameters should be programmed to match the motor's FLA and service factor. Refer to the VFD manufacturer's instructions for details on how to program the VFD overload protection. Sixthly, size the branch circuit conductors. The branch circuit conductors that supply power to the motor and VFD must be sized to carry the motor's full load current, plus any additional loads that may be connected to the same circuit. According to NEC section 430.22, the branch circuit conductors must have an ampacity of at least 125% of the motor's full load current. When using a VFD, the branch circuit conductors should be sized based on the VFD rated input current, which may be higher than the motor's FLA. Determine the VFD rated input current from the VFD documentation. Calculate the minimum conductor ampacity by multiplying the VFD rated input current by 1.25. Select conductors that have an ampacity equal to or greater than the calculated value. Refer to NEC Table 310.16 for conductor ampacities based on conductor size and insulation type. Seventh, size the short circuit protection. Short circuit protection, such as fuses or circuit breakers, is intended to protect the branch circuit conductors and equipment from damage due to short circuits or ground faults. The short circuit protection device must be sized to protect the branch circuit conductors and equipment without causing nuisance tripping during motor starting. According to NEC section 430.52, the maximum allowable size of the short circuit protection device depends on the type of device and the motor's design letter. Consult NEC table 430.52 to determine the maximum allowable size of the short circuit protection device for the specific motor and device type. Select a short circuit protection device that has a trip current equal to or less than the maximum allowable value. 8. Consider harmonic currents. VFD can generate harmonic currents, which can cause overheating of electrical equipment and conductors. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or reactors. Consult with a qualified electrician or engineer to determine if harmonic mitigation is required for the specific application. 9. Consult with a qualified electrician or engineer. Sizing motor disconnects and overload protection with VFD can be complex, and it is important to ensure that the installation complies with all applicable codes and standards. It is always best to consult with a qualified electrician or engineer to determine the appropriate size and type of disconnect, overload protection, and short-circuit protection devices for the specific application. 10. Document the installation. Keep a record of all calculations, equipment specifications, and settings used in the installation. This documentation will be helpful for future maintenance and troubleshooting. Remember that these are general guidelines, and the specific requirements for sizing motor disconnects and overload protection with VFD can vary depending on the application and the local electrical codes. Always consult with a qualified electrician or engineer to ensure that the installation is safe and code compliant. Also, always refer to the VFD manufacturer's documentation for specific recommendations and requirements for the VFD being used. They may have specific instructions for overload settings and protection. Proper selection and sizing are crucial for the safe and reliable operation of the motor and VFD system. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Electrical work can be dangerous, and it should only be performed by qualified personnel. Always follow all applicable safety precautions and codes when working with electricity. Finally, remember that VFD can introduce harmonic distortion into the power system, which may require mitigation measures to prevent problems with other equipment connected to the same system. This may involve the use of harmonic filters or reactors.